So, last time we have discussed the relevance lemma for the first order logic. So, we have stated it in a way that only one interpretation is fixed. Under that interpretation, if you take different valuations which agree on all the free variables of the formula, then it does not matter whether you consider the state with one valuation or the other, right. If one state fixing the one of the valuations is satisfying the formula, so is the other, and conversely. But relevance lemma can also be generalized a bit, like you consider the same interpretation, then there might be some predicates, some function symbols which are not occurring in the formula. So, informally it looks that whatever value or whatever relations you associate with those predicates or whatever functions you associate with those function symbols which are not occurring in the formula, it should not matter, right. So, in other words, you can think of different interpretations, say I is one interpretation, j is another interpretation with the same domain D, right. Now, suppose the maps phi and psi in different interpretations now agree on all the predicates and function symbols that are occurring in the formula, then you can show that any state L under any one of them by fixing the variables will either satisfy or not satisfy accordingly, right. So, that is easy to see, because phi p will be the same relation as psi p. So, it does not matter whether inside the proof you write phi of p or psi of p, anytime you can just exchange between them, right. So, that is the generalized form of the relevance lemma. But then we have told that for sentences something else happens for the relevance lemma, okay. And then if you take the formula p x, whether you go for there exists x p x or for each x p x, they will be sentences from p x by quantifying over the variable x. So, we need, and we told that it might be okay up to certain extent, right. So, for that up to certain extent means what? We have to specify it. So, for that reason we will go back to our usual flow of presentation of the first order logic. So, there we have come across one idea that a state can be a state model of a formula, but we have not yet defined how a formula is satisfied or it is not satisfiable, right. As regards propositional logic, that was our scheme. We go for interpretations, then models, then see how a formula is satisfiable and how it is valid and so on, right. Those are our main target. So, let us start with that today. We say that a formula x is satisfiable if it has a state model, right. So, this means it will be called satisfiable if there exists one interpretation I, there exists a valuation L under I such that the state I L satisfies the formula x. Is that okay? That is what we mean by telling that it has a state model, fine. Otherwise, you will say that the formula is unsatisfiable. So, that means you take any interpretation with whatever domain, whatever map phi is, does not matter, and take any valuation under that interpretation, then the ensuing state I L will falsify it, right. In that case only we will say that the formula x is unsatisfiable. Similarly, you can define validity. So, a formula x is called valid if each state is a state model of x. Okay. So, just like your interpretations in propositional logic, now we are dealing with the state models or interpretations which are states, right. So, in fact, states, we are not telling them as interpretations, is that right. Then you say that a formula is invalid if this does not happen. So, which means you can always find one state which falsifies x, then you say it is invalid. Okay. Now, then we can really generalize this to the consequences also once we have come across this. So, we say that a formula x is given and a set of formulas sigma is given. We want to find out when sigma entails x. So, for sigma entails x, what we need is, let us go back to propositional logic. It says you take any interpretation which is a model of all the formulas in sigma or propositions in sigma, then such an interpretation should be a model of x. That is what it is. Now, we will be dealing with state models, right. So, this one, any state which is a state model of all the formulas in sigma is said to satisfy sigma, right. So, such a state which satisfies sigma has to satisfy x, then we say that the consequence is valid. So, we say that sigma entails x if each state which is a state model of sigma. So, state model of sigma means state model of each formula in sigma. Is also a state model of x. Right. So, if such a state model of sigma exists, we also say that sigma is satisfiable. Let us write it separately. We say that sigma is satisfiable if it has a state model. That means, if there is a state which is a state model of each formula in sigma. So, in such a case we also write the same symbol. Say the state is I L, we will write I L satisfies sigma. That is the way we will be writing. So, it says you consider any state I L, if I L satisfies sigma, then I L must satisfy x. In that case, you say sigma entails x, right. Just like your propositional logic, instead of interpretations small I you are writing there, you are now writing states I L. Okay. If you take two formulas x and y, x and y are called equivalent. So, again we write the same symbol, x is equivalent to y if, now you should be able to do it, if x entails y and y entails x, right, which means you consider any state, that state either satisfies both x and y or falsifies both x and y. Is that okay? So, that means for any state I L, either I L satisfies both of them or it falsifies both of them, right, which we can write this way. It is a cryptical way of writing. Right, because here you are following the same way, if then and everything we are writing, so why not if and only if. So, we go with this, which means that you take consider any state, it is either a state model of both of them or it is not a state model of both of them simultaneously. So, let us see some examples how it goes. So, consider this formula. Now, is it satisfiable? It should be. We do not see any contradiction there. but then to show that it is satisfiable we have to really construct one interpretation, one evaluation, and then show how this happens, right. So, let us go for some interpretation where we will take say I equal to d y, okay. Let us take d equal to say set of natural numbers, we are fond of it now, then say phi of we need only for p and for f, say phi of p is something say less than or equal to, okay, and f is as we have taken earlier say successor function, okay. So, now you can read the sentence in this interpretation, because all that we need for the sentence to be satisfiable or not, one interpretation is enough, we do not need to go for the valuations, but you can keep the valuation does not matter due to relevance lemma, right. So, as it is the sentence now reads every natural number is less than or equal to its successor, right, that is true. So, it is satisfiable, fine, but you have to really go for the states. So, relevance lemma now says that if a sentence is satisfiable, okay, then you need not consider the state, you can simply consider the interpretation, because any state or that interpretation are the same thing for the sentences, okay. Then for the sentences you can really redefine a sentence X is satisfiable if it has a model, not even state model, it has a model, because once it has a state model it will have a model, wherever interpretation the state is that interpretation will also satisfy, fine. But if you want to see, let us say L, say L of x equal to 5, it does not matter now. Now, once you go through everything it will be translated the same sentence, this 5 will never occur, is that okay. Now, that is the satisfiability. What about invalidity or validity? It does not look like that it will be valid, there is no big structure there, right. So, now for invalidity what to do? Again we have to construct one interpretation, right. You just take say p is greater than or equal to, we have done already with successor. So, once you say j equal to d psi, where d is the same natural numbers and phi of psi is say greater than or equal to, now we will take greater than, okay. Let us take the opposite of that, complement of that, even greater than or equal to works. Then phi of f same successor function, psi, right, psi of p is greater than or equal to, and here also psi of f is the successor function, right. So, then what happens in this interpretation, we say that j satisfies for each x p x f of x if what happens, if the sentence will be for each natural number, the natural number and its successor should be related by psi p, right. So, write it as a sentence directly, if each natural number is greater than its successor. If this is true, this is not true, therefore, j does not satisfy for each x p x f x. Okay. So, we say that okay. If we consider states again, does not matter, just take L x equal to something and then J L will be translated to the same sentence again, fine. So, therefore, this is invalid. Okay. Now, what about this sentence? For each x, let us say p x implies p x, it should be valid, right. But to show validity, if you take only one interpretation, that will not suffice, because validity requires you take any interpretation, any state under it, that should satisfy it, right. So, you have to really start abstractly. So, let I be equal to some d phi. We do not have to specify what this phi is, what this phi is, something, it is an interpretation. In fact, here also you need not consider states, because it is a sentence. However, let us start with to go by the definition. So, let L be any valuation under I. Okay. Now, IL satisfies for each x p x implies p x if, by definition, what will it give? Just go by the definition, what does it say, to look at it formally. If and only for each element D in the domain D, right, then we go for the states, new states L, where x is fixed to D. So, you have to see I L x fixed to D should satisfy p x implies p x. Is that okay? Then it will come to I L satisfies for each x p x implies p x if and only if for each D in D. So, now this pi will be written in terms of phi. So, we say that I L x fixed to D satisfies you what p x implies p x. So, it will go to what? L is fixed to D now, right. So, it will say if, it will translate it to English sentence, if x belongs to phi of or D belongs to phi of p, then D belongs to phi of p, that is how it will look. Is that okay? So, that means we may write is D if D belongs to phi of p, then D belongs to phi of p. Right, because x is fixed to D and p becomes phi of p under I. So, I L x to x fixed to D satisfies when this happens, and implies becomes if then in English. Okay. In fact, it is not if then, we should have written if D does not belong to phi of p or D belongs to phi of p, according to our formal semantics, right. So, let us write that way, or that is how we have written the implies, fine, which is true. Okay. So, therefore, we conclude that for each x p x implies p x is valid. So, again when it is valid, we will write the same way as in propositional logic, we will prefix that with the symbol entanglement again. So, this is valid. For equivalence, let us take one more example. Again, okay. Does it happen? See, this one says in abstract terms that there is one y in your domain, there is some particular element d, let us say, okay. So that whatever x you choose does not matter, x and d will be related by p, right. This only asks you whatever element you choose from the domain, you will get some d corresponding to that, right. So that x and d will be related. So you take the same d as earlier, fine. So it should work, but then how to prove it? So you have to start with interpretation. Let IL be a state, where let us say L of x, L of y are given. So we are not writing it, because I we have not specified, where I equal to d phi. Let us start with that. Then suppose IL satisfies there is y for each x p x y. Okay. So once this happens, we want to show that the same IL satisfies the other sentence, fine. Now when IL satisfies this, what do we get? It will say there exists at least one element d in our domain. So let us write it. Then there exists at least one d in D such that for each d prime in D we have d prime comma d belongs to the relation phi of p. This is what it says. Right. See, we want to show IL satisfies for each x there is y p x y. So that means this there exists at least one d, and for each d prime somehow it should commute. Okay. Now how to bring in that? See, if you can visualize this d, for example, let us see as natural numbers, then it will look like 0 d belongs to phi of p, 1 d belongs to phi of p, 2 d belongs to phi of p, and so on. Right? Then we can say whatever the natural number is, that d works. That is how we are thinking. Right? So simply we would say that this d does not depend on d prime here, that is what it says. So you can say it is a vacuous dependence, the same d works for every d prime, right. So then we see that for each d prime in D and the same d we have d prime d is in phi of p. We have just restated it to make it understandable in a better way, that is all. So which says that for each d prime in D there exists d in D such that d prime D belongs to phi of p, which means IL satisfies for each x there is y p x y. Now then it also says something, why the converse does not hold. See, writing this way might give you some problem, that they are just commuting, but they are not really commuting. There is some understanding is going on along with that, it is not just formal writing, right. So, here how to show that this does not entail this? If you just go on writing like that, it will not. You have to give one particular interpretation, where one sentence holds, the other sentence does not, right. That is what we need to show this, not just writing like this and then say the same d prime or the same d may not work for all d, that will not give the answer, right. You have to really give one example now, fine. So, to see this, what we do, take I equal to one particular interpretation we want, n let us say, and some phi, with say phi of p is equality, okay, less than or equal to will do, right. Then this interpretation I satisfies for each x there is y p x y, okay, because what is the reason? It simply is translated to some sentence in this interpretation, it is a sentence, right, we do not have to go to IL now. So, here it is, the translation is what? For each natural number there exists a natural number, say for each natural number m there exists a natural number n such that m is less than or equal to n, that is correct, right. So, for each natural number there is a greater natural number, that is what it says. For each natural number m there exists a natural number n such that m is less than or equal to n, right. But now I satisfies the other sentence, there is y for each x p x y, if and only if what happens? It says there exists a natural number n such that whatever natural number m you take, m will be less than or equal to n. So, there is a maximum natural number, which is wrong, right. Natural number, right, which is false. Therefore, this does not entail the other one. Let us take this equivalence, it sums such of De Morgan, okay, because for all or for each means for each d in d, p d should be true, which is something like p of d 1 and p of d 2 and p of d 3 and so on, and there exists one means for some d p d should hold. So, that means p d 1 or p d 2 or p d 3 and so on, right. So, this is something like your De Morgan's rule. Now, can we show it? Well, we have to try with some interpretation, say I L satisfies not for each x p x. We want to show validity, so no example we will do, we have to start abstractly, right. So, here let us take I equal to d phi, L we need not fix here, right, we can start with I itself due to relevance lemma, fine. So, let us try that way if it goes like that. Now, I satisfies not for each x p x if what happens, it is not the case that for each element in the domain P D holds, D belongs to phi of P, right. See, phi of P is unary here. So, phi of P must be a subset of D, fine. So, this says it is not the case that for each D in D, D belongs to phi of P, which means there is something beyond phi of P, but it is in D, right. So, if and only if there exists at least one D prime in D, but D prime does not belong to phi of P, right. It is just the same thing as that, which does not belong to. So, it belongs to phi P complement, that responds to not. So, if and only if I satisfies there is x not P x, it is clear. Now, let us go back to our discussion on the relevance lemma, where we had one formula P x and we are thinking of which way to look at it. Okay. So, suppose P x is satisfiable. Now, what will happen to for each x P x or there is x P x? Okay, this is the question. Now, let us try. P x is satisfiable. So, that means there is one state which satisfies P x, it is a state model of P x, right. L x we do not know what it is, let us write it as D in our domain. Okay. Here I take I equal to say D phi. Now, when you say I L satisfies P x, it means D L of x. So, D will be coming up, D belongs to phi of P, that is what it will say. Right. This particular element D which L assigns to x must be inside your relation, subset of that relation, subset of that domain D. Okay. Now, will this be true for each x P x? It will say every element is in phi of P, right. P is the totality, P is the whole of D, that is what it says. But will this be true? Because it requires there exists one element D which is in P, that is exactly this. Is that okay? Or if you look at this, you say I of, you say there exists x, P x is satisfiable if for some state say I L prime satisfies there is x P x, that is our definition. So, now I L prime satisfies there is x P x is the same thing as telling I satisfies there is x P x because of relevance lemma, right. So, you may forget this L prime, forget this state, we simply write I satisfies there is x P x for some interpretation, it may not be that interpretation, some interpretation we know I satisfies there is x P x, right. Now, this is done when there is some element in the domain which is in the relation which corresponds to P, that is what exactly told by this I also. It says if I start with this I have D belongs to phi of p, right. So, instead of any other I can take the same I, fine, same phi. So, D belongs to phi of p is satisfied. So, that means P x is satisfiable if and only if there is x, P x should be satisfiable, right. But if you consider validity, case will be different. It is not there is x P x, right. It should be for each x P x, right. Let us see why it is so. See, suppose we take that P x is valid. Once we say P x is valid, it means whatever interpretation you take, whatever state you consider under the interpretation, that state satisfies P x, right. That is what it says. So, now we say I of L satisfies P x for whatever state I choose, fine. Suppose L of x is some D. Now, it says D belongs to phi of p for whatever D I choose. Okay, this is true for every I L, every state. Now, I change the L's, so that every element is now obtained by some L, right. Then that is equivalent to varying this D also. So, whatever D I choose, D belongs to phi of p. So, it is same thing as telling for each D in D, D belongs to phi of p, right. So, for each x P x is also satisfied by the same I, right. But why same I? Any I choose from the beginning, the same way it will proceed, right. If I choose that I, start with that I find that the same I satisfies for each x P x, and whatever I choose does not matter, the same argument still holds. So, that means P x is valid if and only if for each x P x is valid. Okay. Is it clear? So, this argument really we can generalize it a bit. Instead of having only one free variable, we can have many free variables, right. So, you have to go accordingly. Let us give a definition. Suppose x is a formula with all its free variables as x1 to say xm. So, here we are not telling that it has these are the variables which are from the beginning, that x0, x1, x2, we are just making it abstract, some x1, xm, or you can write y1 to ym if it is confusing with the syntax. Okay. Then we write x as x square bracket x1 to xm, just to say that these are the free variables, these are all and only free variables in x, nothing else is there. Just to give that information, we write it this way. Okay. Now, we define that the existential closure of x is there is star x, which is equal to there is x1, there is x2, there is xm, x, x1 to xm. We are just giving another notation, because we do not know what are the variables. So, we will write it this way, there is star x, which means you take any free variable there, existentially quantify over all those free variables, right. Whatever sentence you get, that is the existential closure. Similarly, we will say universal closure. The universal closure of x is for each star x, which is for each x1, for each x2, for each xm, x of x1 to xm. Okay. So, here as we have seen, for p x there is x p x is the existential closure. and for Px, for each x Px is the universal closure. And all these quantifications are done in the beginning, okay, not inside anywhere. Of course, inside will be very arbitrary, where to do we do not know. So, this fixes it. So, our observation can be really summarized. What we have observed from these examples is x is satisfiable if and only if its existential closure is satisfiable. And x is valid when its universal closure is valid. Okay. Is that right? In fact, the way we have introduced the semantics had a bit of confusion. Now, that is removed by this theorem. See, the confusion is this: you consider the formula P x implies P x. If you translate it, okay, it will look like if x is a P, then x is a P, something like this, right. Suppose P stands for x is some man or something. So, if x is man, then x is man, right, but we do not know what x it is. So, without having a particular thing for this x, is it not a sentence also? How do you say it is valid? So, some philosophers will not be able to accept it at all, because x is a variable, it is a named gap, there is nothing there. How can you say if that is P, that is P, right? This should not be allowed, that is what they say. But our semantics says yes, it is valid, because you take any state, we are not taking interpretation, any state I L, that L of x will become some concrete person or some domain, concrete element, right, and this P will become a concrete relation. So, x is a P will have a meaning now, it will say D belongs to phi of P, right. Under any state it will say if D belongs to phi of P, then D belongs to phi of P. So, it is allowed, right. So, interpreting open formulas by states is philosophically debatable, okay, but we need them in programs. So, we have to do it, fine. But now, this theorem says that whatever we have done, whatever confusion we have brought in can be resolved, right. So, in fact, you look at them as sentences by universally quantifying over it. If it is validity, then there is no problem, it becomes a sentence now. It will look like this, and we just say for each x, which is a sentence, right, and this really gives an alternative semantics. There what you do, you just interpret the sentences, do not interpret the formulas at all, interpret only the sentences by translating them into some concrete domain, and you know how to deal with the concrete domain. There is some concept of truth there, right. So, translate it, verify the truth there. Now, sentences can be interpreted, but then how to go for formulas? Through this theorem, right. You say formula, any abstract formula is satisfiable if its existential closure as a sentence is satisfiable. So, you do the other way around, right, that also can be done if needed, and validity similarly can be judged. Is it okay? So, we will not prove it, we have already proved it in this particular case P x, and for each x P x there is x, there is x Px and Px is satisfiable. So, the proof is same, that is the crucial step which will come in the inductive step. It will be done by induction now on the number of variables, free variables in x. I will just give an outline. Suppose there are x1 to xm, xk, number of free variables k, it is okay. If it is 0, it is proposition, it is a sentence, so there is nothing to do, right. Now, suppose for k free variables, it is all right. Now, you have another free variable, right, that is the inductive step. Then what you do? First write x e equal to there exists x k plus 1 and then all the others, right, okay, x k plus 1, only one variable I quantify, fine. Now, what happens? X e is having only k free variables, so your induction hypothesis will apply on x e, fine. So, all that you have to prove is x is satisfiable, this x is satisfiable if and only if x e is satisfiable. Once you do that, you use induction hypothesis and then go for the conclusion on x e, fine. And this proof is that one which we have done, p x there is x p x, there is only one free variable, one existential quantification there. So, same thing will proceed, is it okay? So, proof is not a big thing here. So, all that we have done today is given the satisfiability, validity, invalidity and consequence equivalence, right. Then we have connected the satisfiability and validity with the relevance lemma, right. You see that sentences can always be interpreted directly, okay. So, this gives rise to an alternative semantics, where you first define satisfiability or validity for sentences through interpretations without going to the states. Then open formulas are satisfiable or valid according as their in existential closure or universal closure are satisfiable or valid respectively, right. So, states are not required, that is what the simplified semantics says. You can directly interpret this way, fine. But I told that this is up to some extent. So, that some extent is till we are concerned with satisfiability or validity alone, nothing else, right. But we may require something else. So, states really serve that purpose. That example you can take, if there is a program and something is happening, you have to wait till the termination to decide satisfiability or validity, right. But inside what is happening, you cannot be you will not be able to analyze. But if you have a state concept, you can analyze even what is happening in the next step, even if it has not terminated. That is the advantage, right. So, we are going with this semantics, okay.